Hello and thank you for listening to my talk. Today I'm going to be presenting a talk called To BIC or Not to BIC, Model Selection in Phylogenomics. In this talk I'll discuss some of the challenges we face when using information criteria in phylogenomics and also phylogenetics, and how we can make model selection criteria more generally applicable. Firstly, I'd like to thank Elizabeth Allman and John Rhodes, my fantastic postdoc advisors at the University of Alaska Fairbanks, and the National Institutes of Health who provide our funding. I'll start the talk with a phylogenomic motivation and then talk about how we can use information criteria. This is a yeast dataset of Rocus al. At the top we have a subset of the gene trees with 12 8-taxon gene trees displayed. Don't worry if you can't read the taxon labels or the captions, that's not of particular interest to us. What I want to point out is that not all gene tree topologies here are identical. There are several gene tree topologies displayed here. So what are the implications of this gene tree discord for phylogenetic inference, testing, and model comparison? Why do some gene tree topologies differ from the species tree topology? I previously talked about inference and testing at Phylomania, and today I'm going to talk about model comparison, in particular the AIC and BIC. We can't assume the evolutionary history is identical for all genes. We saw from the yeast dataset that there was no unique evolutionary history shared by all genes. If there was a unique history and all gene tree topologies were identical, then we would have no reason to suspect the gene tree topology to be any different. However, for real datasets, that's rarely the case. If we have discordant gene tree topologies, how do we quantify the discord? How do we infer a species tree? Should we infer a species tree? How do we test a species tree or compare it to a different model such as a network? Unfortunately, we never know the true gene tree topologies. Instead, we must use inferred gene tree topologies. These gene trees are likely to have some inference error. One way to model gene tree discord is to assume that all gene tree topologies are identical and any discord in inferred gene trees is due to inference error. Unfortunately, to our knowledge, there is no way to easily test gene tree inference error or to compare these models to models assuming other sources of gene tree discord. While gene tree inference error is likely to be a contributor to gene tree discord, we ignore it here since it's very difficult to model. An alternative explanation of gene tree discord is the process of incomplete lineage sorting, which we'll discuss here in more detail. Unlike with inference error, we can test incomplete lineage sorting and compare the models to others. In many datasets, it's likely that both inference error and incomplete lineage sorting are contributing to gene tree discord. I'll explain incomplete lineage sorting, which is modeled by the multi-species coalescent, with an example. Here's a 6-taxon species tree, the tree with the thick edges. Inside the species tree is a rooted 6-taxon gene tree in pink. We're going to assume there is only one lineage per taxon for simplicity, but this isn't a requirement of the MSc, it's simply to make things easier for us. Then starting at the bottom of the species tree, we have a single gene lineage in each leaf of the species tree. Working up the species tree towards the root, eventually we pass vertices of the species tree, representing the most recent common ancestor of the taxa below it. Above these vertices we have multiple gene lineages present on the same edge of the species tree. With multiple lineages present on the same edge, coalescence can happen where pairs of lineages merge according to a stochastic process. Eventually, the last pair of lineages coalesce at the root of the gene tree. Note that coalescence can happen above the root of the species tree, and the root of the gene tree cannot be below the root of the species tree. We've highlighted the quartet gene tree involving taxa A, B, C, and D because it's the set of all quartets that we'll be interested in modelling, and this is one example of a choice of 4 taxa. When a pair of lineages coalesces into a single lineage, we call this a coalescent event. Coalescent events follow a Poisson process, with the rate being an increasing function of the number of lineages present on the species tree edge. There's an exponential waiting time for the first coalescent event, with the rate again being an increasing function of the number of lineages. Simply put, the more lineages present on an edge of a species tree, the more likely some pair coalesces in a short period of time. Each pair of lineages is equally likely to coalesce, and once a pair of lineages coalesces, the new lineage is treated no differently to the other remaining lineages present on that edge, regardless of how many taxa that lineage represents. Finding expressions for the probabilities of gene tree topologies is generally extremely difficult. However, if we restrict ourselves to quartet trees, which are trees displaying 4 taxa, then it becomes easy. We choose a set of 4 taxa and restrict the rooted species tree to the subtree displaying only this quartet. We then find the probabilities of rooted quartet gene tree topologies. Finally, we marginalize out the roots of the species tree and the gene trees to obtain unrooted trees. We find that the gene tree topologies are multinomially distributed, with probabilities being simple functions of the single internal edge of the species tree, which is the edge labeled T. The gene tree topology concordant with the species tree topology has probability at least 1/3, and the other two topologies have equal probabilities no greater than 1/3. The relative frequencies of the gene tree topologies can be used to estimate the internal edge T of the species tree. The longer the internal edge, the less gene tree discordance there is. We can then find these probabilities for all sets of quartets. We can compare models with and without assumed species trees. Two models we're interested in are the T1 and T3 models of Mitchell et al. The T1 model assumes a specific unrooted quartet species tree topology. The T3 model assumes one of the 3 possible unrooted quartet species tree topologies. For model T1, the first probability is at least 1/3, and the other 2 are equal and no greater than 1/3. Whereas for model T3, because the species tree could be any one of the 3 topologies, any 2 probabilities are equal and no greater than 1/3, while the remaining probability is at least 1/3. For simplicity and in the interest of time, we're only going to look at model T1 in detail in this talk, and not T3. We compare the models with assumed species trees, so that's model T1 and model T3, to models without. Typically, we're only interested in one of model T1 and model T3, and we define the full model relative to it. We define the full model to be all probabilities inconsistent with model T1 or model T3. If we select the full model over model T1 or model T3, this could mean that the or a species tree is a poor model. In order to perform model comparison, we need an understanding of the geometry of the parameter spaces of the models. In the full model, there are 3 probabilities, 2 of which are free to vary, with the third being the remainder needed to sum to 1. Then the full model lies in the open 2-dimensional probability simplex, which are the equilateral triangles displayed here on the left and right. The vertices of this triangle correspond to the probabilities 1, 0, 0, 0, 1, 0, and 0, 0, 1, and the centroid in the middle of the simplex corresponds to the probability 1/3, 1/3, 1/3. Since there is only one parameter for model T1, the internal edge of the species tree, the parameter space must have dimension 1. It's the line segment from the centroid to the top vertex on the subfigure on the left. For model T3, there are 3 line segments, each representing a species tree topology, and each from the centroid to one of the vertices. So that's the subfigure on the right. The closer gene tree topology frequencies are to the line segment or line segments, the higher the likelihood of model T1 or model T3. In previous talks, I've talked about model T1 and model T3 under a hypothesis testing framework, but we could compare one of these models to the full model using information criteria as well. Susko and Roger identified some problems that need to be addressed before information criteria can be used in phylogenetics and also in phylogenomics. Information criteria cannot be assumed to perform well when parameters are constrained, such as true parameter values that are small and cannot be negative. Examples include short species tree edge lengths and small substitution rates. If there's only one thing that you take out of this talk, it's this. Short species tree edge lengths not only create inference problems, but they also create model comparison and testing problems. It's all due to the uncertainty that we have over the species tree topology. These issues not only exist in phylogenetics and phylogenomics, but in many diverse research areas where models have constrained parameters. Information criteria are typically in the form of -2 times the logarithm of the maximum likelihood plus some penalty term. The penalty term is an increasing function of the number of parameters to avoid model overfitting. We also want information criteria of this form, but the challenge lies in finding appropriate expressions for the penalty terms, which people often assume to be arbitrary. However, these penalty terms aren't at all arbitrary and they have deep mathematical meaning. In order to find expressions for the penalty terms, we typically have to assume parameter spaces have no singularities or boundaries, which are points where sections of the parameter space end abruptly or intersect with each other. Examples of singularities and boundaries of parameter spaces are points where the species tree edge length is 0. So this is the centroid of our probability simplex, where the probabilities are 1/3, 1/3, 1/3. This point creates problems because the model T1 and model T3 parameter spaces here are not smooth, they end abruptly. We need to generalize our information criteria to allow for singularities and boundaries by generalizing the penalty terms. And here we're going to generalize the AIC and the BIC. The Okaike information criteria, or AIC, is one of the most widely used information criteria. It seeks to find the candidate model with the smallest expected Kullback-Leibler divergence from the unknown truth. The Kullback-Leibler divergence is a measure of how close two probability distributions are to each other. The AIC is a consistent estimator of the expected Kullback-Leibler divergence. The candidate model with the smallest AIC is selected, or candidate models with lower AIC are weighted more heavily. For regular models with no singularities or boundaries, the AIC is -2 times the logarithm of the maximum likelihood plus 2 times the number of parameters. So now we're going to have a look at how we generalize the AIC to allow for singularities and boundaries. After we ignore arbitrary constants that cancel out when taking differences in AIC values between different models, the Kullback-Leibler divergence between the unknown truth and an arbitrary parameter is the expected value under the truth, that's the E subscript naught, of -2 times the logarithm of the likelihood at the arbitrary parameter theta. Then the Kullback-Leibler divergence between the unknown truth and the MLE is found by simply substituting in the MLE for the arbitrary parameter. Then finally, the thing that we're interested in, which is the expected Kullback-Leibler divergence, is the expectation under the truth of this quantity. By using the MLE, we minimize the expected Kullback-Leibler divergence and in turn the AIC between the unknown truth and the candidate model. We want the AIC to be a consistent estimator of the expected Kullback-Leibler divergence between the unknown truth and the candidate model. To do this, we can set the AIC to be -2 times the logarithm of the maximum likelihood, which is the first term here, plus the expected Kullback-Leibler divergence, which is the second term, minus the expected value of -2 times the log of the maximum likelihood, which is the third term. Then when we take the expectation of the AIC, the first and third terms cancel out, and all we're left with is the middle term, which is the expected Kullback-Leibler divergence. So then this form of the AIC is more general than the standard form, and we can adapt it to models with singularities or boundaries. We can arrive at a more general form of the AIC that is valid for models with or without singularities or boundaries. This form of the AIC is, as expected, again, -2 times the logarithm of the maximum likelihood, which is the term on the left, plus a penalty term, which is the term on the right. We assume that our random variables, or data, which we denote x subscript n, are normally distributed under the central limit theorem. Then the penalty term is an expectation under the truth, E0, involving the sample size n, the mean of the random variables x bar, the true parameter value theta naught, the MLE theta hat n, and the Fisher information matrix evaluated at the true parameter point theta naught of I of theta naught. Roughly speaking, the Fisher information matrix is just the inverse of the covariance, so you can think about it that way if it makes things easier. Theta naught is the vector of true gene tree probabilities. Theta hat n is the vector of MLE, gene tree probabilities, under the candidate model. And x bar is the observed relative gene tree frequencies. The penalty term represents how close the random variables and the MLE are to the true parameter point, roughly speaking. This form of the AIC is equivalent to the standard form for regular models with no singularities or boundaries, but the advantage is that it converges more quickly to the expected Kullback-Leibler divergence than the standard AIC does, and also that it can be interpreted as a small sample correction to the standard AIC. The disadvantage is that it's harder to use and it can be very difficult to use for complicated models. Fortunately, our models are pretty simple, so we can actually make use of it. So what is our generalized AIC for model T1? For model T1, the penalty term is just a simple increasing function of the internal edge length T of the species tree in coalescent units. The penalty term is 1 plus ERF of mu naught divided by root 2, where ERF is the error function and mu naught is an increasing function of the edge length T. So we can kind of think of mu naught as some kind of transformed edge length. Unfortunately, T is unknown, so we have to estimate the penalty, which we can do using the MLE or some other means. And the penalty ranges from 1 when the edge length T is 0 to 2 as the edge length T diverges towards infinity. Roughly speaking, this means that the T1 model behaves as if there is half a parameter when the edge length is 0, 1 parameter when the edge length is infinite, and something in between for positive edge lengths. Now we'll move on to the BIC. The BIC has a very different motivation to the AIC, but again, it's just -2 times the logarithm of the maximum likelihood plus some penalty term. BIC was first introduced by Schwartz, and it's -2 times the logarithm of the posterior probability of the candidate model conditioned on the random variables. We select the model with the highest posterior probability. For regular models, the penalty term is simply the number of parameters, k, multiplied by the log of the sample size, n. Starting with Bayes' theorem, we can find an expression for the posterior probability of the model conditioned on the random variables. That's P of m given xn. The likelihood function L of xn given m can be expressed as a function of the parameter theta, so that is as L of xn given theta and m, multiplied by a prior probability distribution for parameter theta given the model, that is pi of theta given m, and then integrated over the parameter space theta. We can ignore several of the probabilities in the previous expression. Firstly, after we take -2 log of P of m given xn, the prior probability of the model, that is negative 2 log p of m is O of 1, which means it doesn't grow with the sample size. However, there are other terms which are O of log n, which do grow with the sample size. So we can just assume that p of m equals 1 or negative 2 log p of m equals 0, since asymptotically it doesn't contribute to the expression. We can also ignore p of xn since it's independent of the model and therefore cancels out when we take the difference in expressions from two different models. We can ignore pi of theta m since the likelihood concentrates increasingly near theta hat n, and again we can take pi of theta hat m equals 1 or negative 2 log pi of theta hat n given m equals 0 since it's again O of 1. So the more general form of the BIC, than the standard form then follows. So we can obtain the more general form of the BIC that is valid for models that have singularities and boundaries as well as regular models. The penalty term here, which is the second and third terms, is found by integrating out the parameter space of the candidate model. Again, the penalty is a function of sample size n, the mean of the random variables x bar, and the MLE theta hat n. The BIC, however, does not depend on unknown true parameter theta naught, since we instead have a prior distribution placed on the parameters theta, which we then integrate out. So the penalty term is again a function of how close the random variables are to the MLE, and the further the random variables are from the MLE, the larger the penalty term and the BIC. Again, the generalized BIC is equivalent to the standard BIC for regular models, converges more quickly to the negative 2 log posterior probability of the model, conditioned on the random variables, and can be interpreted as a small sample correction to the BIC. So let's have a look at the BIC for model T1. It looks quite nasty, but it can be computed quite easily. So for model T1, the penalty term for the BIC takes one of two possible values depending on whether the random variables are in the parameter space. So the penalty ranges from a minimum of log n when the maximum likelihood estimate of the species tree edge length diverges towards infinity, to diverging towards infinity when the random variables lie a long way below the centroid in the probability simplex, indicating that a different species tree topology has a higher likelihood. So if we have an extremely high BIC without a particularly high n, then it probably means a different species tree topology has higher likelihood, or that all of the species tree topologies are poor. We're looking at an example of swordtails and platyfish of the Ziphophorus genus from Cui et al. The authors concluded that there was evidence of widespread hybridization amongst these fish. This dataset has 24 taxa and a sample of 1,183 gene trees. There are 24 choose 4, which is 10,626 sets of species trees. So we can compute the generalized AIC and generalized BIC for each of these quartets. We compare either model T1 or model T3 to the full model. Again, for simplicity, we'll consider only model T1. We first infer a 24 taxon species tree topology, which we won't show here, which will determine all of the displayed quartet species tree topologies for model T1. Here's a random sample of 10 of the 10,626 quartets. We define the difference in AIC as the AIC for the full model minus the AIC for model T1, and the difference in BIC similarly. Regardless of whether we use the AIC or BIC, we find that the full model is often selected over model T1, and that the correlation between differences in AIC and differences in BIC is very close to 1. We choose the full model 56.5% of the time when we use the AIC and 30.9% of the time when we use the BIC. We have a large percentage of quartets where we're choosing the full model over model T1 of a specific species tree topology and the multi-species coalescent. This could possibly be due to species tree topology being a poor fit, which will be consistent with the conclusion of QE-AL of widespread hybridization. But of course, there could be other causes as well. Both the AIC and BIC have advantages and disadvantages relative to each other. So which one should we use? One disadvantage of the AIC, when we generalize it here, is that it depends on the unknown true parameter, which we need to estimate with the MLE or by some other means. Whereas an advantage of the BIC is that it doesn't depend on the unknown true parameter since the parameter space has been integrated out. The AIC requires no assumptions on prior probabilities, while the BIC, which is Bayesian, does. We were able to justify that the prior probabilities do not have any impact asymptotically on the BIC. However, for finite sample sizes, these prior probabilities do have an impact. Some would consider the presence of prior probability distributions an advantage. However, with the lack of any obvious choices for the prior probabilities, then we might consider this to actually be a disadvantage. The AIC is not statistically consistent and will not generally select the candidate model containing the truth asymptotically with probability 1. On the other hand, the BIC is statistically consistent. While statistical consistency is a nice property, if we have no reason to assume the truth is among any of the candidate models, then we may not care about statistical consistency. Whether the AIC or BIC is preferable according to this criteria depends on whether it can be assumed that the truth or something close to it is among the candidate models. And finally, the AIC penalizes smaller models more than the BIC, which penalizes larger models more than the AIC. So again, which is preferable depends on what we want to achieve. So which one should we use? Both are useful, and perhaps it's better not to actually just choose one and to use both of them. If we use both and they're in agreement, then this is a stronger result than considering only one of the criteria. If the criteria are not in agreement, then the context of the problem could be used to decide which criteria we want to choose or which criteria we want to weight more heavily. The BIC appears to select the model of a species tree with the multi-species coalescent more often than the AIC. So since this is the simpler, less parameter-rich model, perhaps we should choose the BIC in this context over the AIC if they disagree with each other. For future work, these generalized AIC and BIC will be implemented into the MSc Quartets R package of Rhodes AL, and the model selection will be generalized to N taxa. Thank you for listening.